Okay, so this week we are going to finish a discussion of interference. We will specifically talk about anti-reflection coatings, Michelson interferometer, Mach-Zehnder, a couple other interferometers, and then some applications, including multiple beam interference. And I doubt we'll have time today, but I'm hoping we can get into at least the general considerations of diffraction, at least in the next lecture. Let's see how far we get today. Okay, so what is an anti-reflection coating? The basic idea is that there are many situations where we do not want a reflection from a surface. Specifically, you can imagine that you have a laser beam that is going into some system where you are trying to measure some properties. You don't want to lose some of the laser power and just reflections from glass surfaces. Along the way, things like the National Ignition Facility, we're trying to do fusion experiments. Those lasers are like super powerful. And if even a tiny amount of light is, reflected off of like some of the windows and things like that that the laser beams have to go through, that amount of energy, you'll be losing all that energy as it goes into the system where you're actually trying to make a fusion or some other thing. And also B, the reflected energy is so powerful that, it's basically a hazard for a lot of other things as well. So, there are many applications for anti-glare, anti-reflection, etc., many of these technologies. So the simple idea is that we have a film of certain thickness and a certain refractive index, NF, in between the air, which is typically the incoming medium, but it could be anything, of course. So let's call that refractive index N0 and NS. NS is usually referring to a substrate like glass from which we want to reduce the reflections. Okay. And you can immediately see there will be two reflections, E1 and E2, right? And what we want here is that we want E1 and E2 to destructively interfere with each other, thereby giving rise to the term anti-reflection coating. Okay. And so the first question you have to ask yourself is, what should be the thickness and what should be the film refractive index to achieve this task? Well, the film thickness, as we can imagine, is that we want to introduce a pi phase shift between the beam E1 and the beam E2, right? And assuming that NF will be somewhere in between N0 and NS, right? You might guess without thinking about it, NF is like, say, the average of N0 and NS, okay, without too much thinking, because you're just like, okay, it's something that has to give some reflection from here and some reflection from here. It can't be greater than this NS probably, because then you will only get a reflection at the critical angle. And here the angles are, much lesser perhaps than the critical angle, for example. Okay, so NF is somewhere in between N0 and NS. That's the first obvious or intuitive picture, hopefully, that you have already. And now we want to introduce a phase shift between this and this of pi. So for that to happen, what should be the thickness H, such that you get a phase shift of pi between E1 and E2? Does anyone have a suggestion? How much should this H be? Saying also the fewer people, what I see. Yes, what's going on here? Is there some event today? That's good, because I have a pop quiz that only you people will be able to access today. I showed up for the class, and you'll have the secret answer. Okay, so anyone have an idea how much H should be? Should it be dependent on a parameter that you have all come to know and love by now about the wave? What parameter of the wave? Yes.
The wavelength.
Wavelength. And so, excellent. So now what? Should it be a multiple of the wavelength? Should it be a fraction of the wavelength? What are we thinking? How many times does the beam go through the thickness H? Or how much distance in the film does it travel? Yes.
2 times.
2 times H, right? At normal incidence, it's 2H. Of course, if it's an angle, then there's some factor of the angle. So now 2h, which is the should be what to give me destructive interference. About this last class also. When do I get destructive interference? How much difference in the phase? I mean, what parameter will govern whether there's a phase difference of pi or not for this extra path length? Equal to, yes? Half a wavelength, exactly, very good. So it should be half a wavelength in this film. Is everybody okay with that? Why it's half for destructive interference? It's not. Stop me now. You can think about it as if there's a half wavelength, then the wave has gone forward by pi. Just think about the picture of the wave, right? It's gone forward by pi. Okay. So, and of course, one slight subtlety is that the wavelength that matters is the wavelength in the film, not the wavelength in it. Okay, because the wavelength in the film, as you know, is different from the wavelength in air due to the refractive. Okay, this is all taken care of as another way of saying that is that the optical path length that this thing travels is 2 pi over is 2 times NF times H. That's the optical path length, not just the geometric path length. Okay, and that should be then equal to m lambda naught over 2. So that will also give us the same answer. So H equals lambda then over 4, lambda here representing lambda naught divided by NF. Okay. Maybe I should write that. The next thing we want is for perfect destructive. Yes.
Could you explain again why it's a fraction of the wavelength?
Oh, okay, sure. So, how would you like me to explain this? With a physical picture or with like math, or what's the best way you learn?
I don't understand it conceptually.
Okay. All right. So let's talk about going back to 2 waves. Okay. This is wave 1. Okay. And this is as a function of position x. Okay. And then wave 2 is just like this, except it's shifted by the path length difference. Okay. So we want, for destructive interference, we want that, say, the maxima of this one to coincide with the minima of the other one to give me destructive interference. So if I were to draw that wave, it would have to do something like this. And now you can see for every maxima, there's a minima. When I add these up together, I get basically 0 for the sum. Okay. So if I want this to shift the wave by this half a period, right? So 1 period in spatial domain is the wave, right? Because if I shifted this whole wave by 1 period, which is lambda in the spatial domain, I would get the wave back, right? Everything would coincide. So to make it shift half of that, I need to shift the wave by lambda over 2. Does that help? Okay, so now we know that a path length difference of lambda over 2 will give me destructive interference. It can also be 3 lambda over 2, 5 lambda over 2. So I take lambda over 2 and add lambda to it. That will also give me destructive interference because that just shifts everything by 2 pi again. Okay. Is that part clear? Okay. So now we want to ask, what is the extra path that the wave traveled in the medium where it was? Okay, so we have the medium, which is this film with a thickness h. Okay. Well, the first ray or the first wave just reflected right off the top of the film, so it doesn't travel in the medium. The second one travels a distance h going down and a distance h going up for small angles, right? It's almost h. Okay. So the second ray then has traveled the distance 2h. Okay. And we just agreed that if this wave has to destructively interfere with the first one, we want to shift it by lambda over 2. So this must be equal to lambda over 2, except that, as I was saying, there's a subtlety that this must be the wavelength in the film, not the wavelength in air. Okay, and therefore this must be lambda naught divided by NF time divided by 2, which is lambda naught by 2NF.
Should this be 2 over lambda multiplies the odd number? This is the first.
Say that again.
So is this the first? So is this the first order? Is this just the first order so that we don't have?
Yeah, this is just the first order because that's the easiest one to design usually. Like, you know, you want the thinnest possible thickness on the material. You may not want to adjust the material too much for the anti-reflection coating. Of course, you can make it thicker by equating this to 3 lambda of 2.
This is a coating, the coating, so we want to make it as thin as possible.
Exactly.
So that's why we.
Exactly.
Okay. So
Right.
This is the context.
Right. The other way that we can equate this is just going back to the math, which is cos kz minus omega t. And then, so this z, this optical path length difference is again given by 2 pi over lambda naught times z. Okay, where z is this extra path length that we have traveled, so call it h, for example. Well, again, as I said, in the medium, we must replace this by lambda f, which is the, so this is equal to 2 pi over lambda naught times nh, nfh. This part is called the optical path. So just take the geometrical path length and multiply by the refractive index is the optical path length. We also saw this when we discussed Fermat's principle. And again, the same argument, this must be equal to some pi. If we want an extra phase shift of pi, that immediately will give you the same answer that we just came up. Okay. Well, I guess it's 2h because it travels twice in the medium. So hopefully both of these approaches help you.
Yeah, thank you.
So the other point that we kind of assumed was that the two amplitudes are also equal because remember when I drew the wave, I drew them both to be the same height on the blackboard just that I just hidden. You know, I had the two waves of nearly the same amplitude height. That's because then you get perfect destructive interference or perfect constructive interference. If they are not the equal amplitude, then you won't get perfect destructive or constructive interference. So to ensure that, I need to set the amplitude of this reflected wave here and reflected wave here the same. To do that, I can use the Fresnel coefficient that we derived in an earlier lecture. This is the Fresnel coefficient for reflection at the first interface. I'm assuming nearly normal incidence. So I've set all the angles equal to 0 degrees, basically. So otherwise there would be like cosine theta, sine theta, etc. Over here, all of those are set to basically 0. So we get just NF which is this guy minus this guy divided by NF plus N naught. That's the reflection coefficient at the first interface. And then the second interface is similarly NS minus NF divided by NS plus NF. That's the reflection coefficient at normal incidence, just from Fresnel's formula. Okay, so equating these two, because we need equal amplitudes, we obtain a very important relationship, which I said NF is now not the arithmetic mean, not the average of NS and N naught, but the geometric mean. That's what this relation tells us. So we kind of intuitively said, NF must be somewhere in between N naught and NS. Probably it's the average of the two. It turns out it is an average, but it's the geometric average, geometric mean. Anyway, that's not important, super important, because of course you may have situations where you're not at normal incidence, and then of course you will have to like derive or figure out what these refractive index should be. But usually, at least at normal incidence, you would like perfect anti-reflection coating. And then when you go off of normal incidence, this thing falls off a little bit. It's not as perfect anymore. Okay. But this is very useful, and this is a very important application of anti-reflection coatings, that we design this film thickness to be as thin as possible. It's just the wavelength lambda naught divided by NF and 4 times NF, right? And from that relationship. And then the refractive index of this coating is then given by NS N naught square root. Okay. And for glass, there are many materials which end up that we can coat with various vacuum UHV material science techniques. We can coat thin layers. This will end up being, obviously this is going to be on the order of like 100 nanometers or less for like green light. So it's a very thin layer, very thin coating. And also the refractive index is usually, it has to be some material that will stick well to glass, it's hard and so on. So there are a few other materials, magnesium fluoride, etc. These are well-known coatings that people use for glass. Yeah. Obviously, this makes the thing more expensive to get really nice anti-reflection coatings. So that was the first application. So now I want to talk about another device that's very important, and it also from interference we can understand what this does, which is the Michelson interferometer. And yes, indeed, this is the interferometer that Michelson and Morley used when they measured that or showed that the speed of light or that the ether, so to speak, does not exist. Okay, so what?
Historically, so I think it was trying to move the speed of the speed of the Earth. So
yeah, they were trying to. They said if there is an ether through which electromagnetic waves propagate, right? I mean, so as we know, most waves seem to propagate in a medium, right? Like we have sound waves, we have water waves, we have sound waves in a metal, etc. There are so many types of waves, right? So when electromagnetic waves were first discovered, I mean, when Maxwell first figured out that a light is just an electromagnetic wave, the question became, what is the medium in which electromagnetic waves propagate? And so it was very natural, right, intuitive for someone to say, well, there must be a medium in which electromagnetic waves propagate. What is that medium? Well, we can't seem to see any medium. I mean, on Earth, it's air, but what about from a star or some other place? Where is that medium? They postulated that there's a medium called ether, okay, the luminiferous ether, as it was called. Okay, I hope you all understand now why they postulated it, because it is just intuitive to say that a wave must propagate in some medium. Okay, so this wave, this ether that they said must exist. Well, now if the Earth, of course, is traveling through space around the sun, then maybe there's a relative velocity between the ether and the Earth, which means that the speed of light would be different in one direction relative to another direction. Well, the one traveling, in this way versus the other way, because it's propagating in the ether. And then they said there must be an ether wind. Basically the Earth is being, subjected to an ether wind, because just like if I were to go outside and run, I feel like a wind in my face. The relative velocity between the Earth and the ether would cause an ether wind, which would then cause the light to change its velocity. And so that's what they were looking for in this very careful experiment, the Michelson-Morley experiment. And they found no change in the velocity. So anyway, okay, so that's a little bit of a digression, but the point is, okay, let's look at what this Michelson interferometer is. You're already familiar with it from the lab, but let me just go over it quickly. So we have a source. We may put a ground glass or something to like just make the source more extended and diffuse. And then we have a beam splitter, which I'll show you in a minute. It's just a piece of glass with a thin layer of metal. The thin layer of metal basically reflects some of the light and transmits some of the light. Okay, at least that's how beam splitters were made back then. Okay, so partially silvered mirror, as it is called. Okay, and so that's the beam splitter. So half of the light goes straight through, hits a mirror over here, which is called M1. Ignore the C for now. Just ignore it. It's not there. Imagine it's not there. And then it comes back and reflects here and goes to the detector or the person who's observing with, say, a lens, the viewing area of this beam splitter. Okay. And similarly, the other beam, which was reflected from that partially silvered mirror, goes to this mirror and comes back and then hits the detector or the person's, who's viewing it will observe it when they put their eye over there. Okay, so we can see now that there are two beams or two waves that propagate along these two paths. Obviously, this path, if it is slightly longer or shorter, the wave will have a different path length here versus here. It's a very straightforward idea for what this experiment is doing. And now we have one subtlety. So we have this beam, ignore this reflection. This is called a ghost reflection. I talked about it when I discussed mirrors, that, when you have partially silvered or second surface mirrors, as they're called, there's not a first surface or front surface mirror, not a high quality mirror really. When you have that, then you'll have this initial 4% reflection from a glass. Any glass has like about 4% reflection from it. So, but ignore that reflection. Now let's look at how many times this beam goes through this piece of glass. It goes through once, twice, and then it goes up there and comes back again through the glass. So it goes 3 times through that thin layer of glass over there, which is in the beam fluid. Whereas this other beam, if you didn't have this compensator C in present, it would never go through it would go through the piece of glass just one time. Just in that first transit, it goes through, hits the mirror, comes back, and then gets reflected. So you can see you're already introducing a path length difference into the system, even if these two mirrors were exactly equidistant from the beam fluid. So to compensate that, they introduced an additional plate of glass, which is the exact same thickness as this one, except it does not have any partially silvered surface at the bottom. So it just transmits the beam and brings it back. Okay, so that's the compensating plate that we introduced also in the lab. You must have noticed this compensating plate. Okay, so that was that's just summarizing what I just said. Okay, so if you redraw the system, and how do we redraw it? Well, imagine that you place yourself at the detector and you're watching the entire system in this perspective. Then this mirror, because it's reflected here, right, at this surface, look, there is an image of it over here. Okay, we can clearly see that, right? It's as if this mirror was put over here. So it's an image of this mirror. So M1 prime is the image of this mirror in this path over here. Similarly, we can draw an M2 obviously is also has a it is also seen through that surface, and finally the source can also be viewed through that mirror, the O, which is over there, the partially silvered mirror, which is over there. So we've just basically redrawn the system as if it was in a straight line. So here's the source, which effectively is in the plane of the beam splitter, and then we have M1 prime, which is the reflection of that mirror M1 in the beam splitter. And then M2 is of course just whatever M2 is, wherever M2, as you would see through the beam splitter, that distance to M2. So this is the distance effectively, if you like. I have laid out the distance from S, the source, up to the mirror M2. That is just what is written over here, S0. Okay, this is S0, which is I've just laid it out in a straight line. Okay, and then S0 prime is just the distance of the source to the mirror M1 prime. Okay, and and everything else is the same. So of course, since these two are two mirrors, the image of the source in mirror M2 will be a distance Si, which is equal to S0, right? And that is this guy over here. Okay. S2 is just a point. If this is a point on the source, then it will be imaged to this point, S2 prime over here, or S2 over here. Okay. Similarly, S1 is the image of S in M1 prime, which is over here. Okay. And now you can also see that the difference between these two planes, where the source plane, the image plane of the source in M1 and M2, this distance must be now 2D, right? Because it basically, the mirror is going to cause that, that distance. Or you can think of it as the beam went through the distance D, which is the difference between the distances of M1 prime and M2 twice. So it goes through it twice. So that's like 2D. Okay, so and then so this looks again just like our parallel plates. And so again, we can apply the same Heidinger fringe argument of like, you know, it must be 2D times cosine of the angle, just like we did for the anti-reflection film. If there was no angle, then this would be just 2D. But if I'm viewing it at some angle, theta, then it will be 2D cosine theta. Okay, this is just like that earlier situation. So we get interference fringes because this looks just like the situation with the Heidinger fringes or the anti-reflection coatings or the films, etc. It's exactly that same situation, and we get therefore circular fringes, which is also what we said when we have Heidinger fringes and fringes of equal inclination. All the fringes at the same angle theta, or all the points at the same angle theta, which is symmetric around this optical axis, will be having the same path length difference, 2D cosine theta. And now, if we didn't have any phase shifts, then this 2D cosine theta for constructive interference, bright fringe, what should I set that equal to? Let's assume there are no phase shifts at the mirrors for a moment. Then when will I get constructive interference? And 2D cosine theta equals? Is it now lambda over 2?
No, it's theta. It's the theta over. It's cosine theta over 2. Things so before.
No. It's still cosine theta.
Yeah, I think. Well, I think the theta we should. Oh, okay.
So what should that be equal to in terms of the wavelength for constructive interference? We just talked about it. For destructive interference, it should be equal to?
For 2 over lambda over 2 multiplies the odd number.
Exactly. So for destructive interference, we have lambda over 2 or 3 lambda over 2, 5 lambda over 2, just like the anti-reflection coating. For constructive interference, what should I get?
Then lambda over 2 multiplies even number.
Even number, right? Or equal to lambda, one wavelength. Because as we said, when I move the wave by one period, which is one wavelength in the spatial domain, I'll reproduce the wave and I'll get constructive interference. Okay, so, okay. But this just summarizes, but there's one caveat, which is again going back to this picture here. We can see that the beam undergoes one external reflection. So basically, and then one internal reflection, meaning when I come here for this beam, it's undergoing an internal reflection because it's within a glass, which is a higher refractive index, and lower refractive index, which is air. So there's one internal reflection. So it's actually 180 degree out of phase with respect to the other reflection, which means that everything I just said will switch. We'll get a destructive interference when the two beams are a multiple of lambda, m lambda. Okay, so normally we would have expected that to be just 2D cosine theta equals m lambda, would give me constructive interference, bright fringe. But because I have this one phase shift of 180 degrees at the two interfaces between the first beam and the second beam in the beam splitter, therefore we get destructive interference. So we get dark fringes when 2D cosine theta equals m lambda naught. Okay. So again, these are fringes of equal inclination. And so if you have a large lens there that you're looking through, then you'll be able to see the entire pattern of the fringes in the Michelson interferometer. So, you know, of course you can use your eyes, but a lens will usually help to view that pattern. Okay. Okay. This is just showing that same picture from the perspective of the person watching. All right. So now imagine that instead of just keeping M2 fixed, we moved it, right? So we translated it, right? D, let's say M2 is moving towards M1 prime, okay, in this picture over here. Okay. So M2 is moving towards M1 prime, D is decreasing, right? Okay. So the cosine for the same M, if I fix the same fringe maxima over here, M is fixed, and I'm tracking that one fringe, D is decreasing, then cosine theta has to increase to preserve that M. Okay, which means the fringe will shrink toward the center because cosine theta increases as theta decreases. So the ring will move towards the center as M2 is moved towards M1 prime in this situation. Okay, so when D decreases, the rings will start to shrink toward the center, and obviously the other way. What happens to the central point? Because see, as D decreases by half a wavelength, right? Then the highest order fringe can no longer be obtained at the center, right? Because now it has nowhere else to go. It wants to shrink towards the center, but it's already at the center. Remember, the highest order fringe in Heidinger fringes is at the center. That is basically when cos theta equals 1, which is the central point. That's the highest order fringe because 2D equals M lambda naught. And any other fringe outward from that will be lesser in the order. So the highest order fringe cannot be obtained as D decreases by half a wavelength. So a fringe will disappear in the center, and a new and the fringe that was earlier at say the first maxima will move inward into the center. So this is how you have to argue or think about what will happen as D decreases or increases in the Michelson interferometer. Just remember this way of thinking about it because this is something that will commonly pop up on homeworks, tests, etc. Okay. Okay, so I'll just finish up by saying when the mirrors are perfectly parallel, if I adjust the mirrors so that they are perfectly parallel to each other, you get the Heidinger or circular fringes. But you can make the mirrors not parallel to each other. For example, if the mirrors are slightly tilted with respect to each other, now it looks like a wedge. Okay, the two mirrors are now like a wedge. You'll get Fizeau fringes, which are fringes of equal thickness. So you can, when there's a small angle between the mirrors, it looks just like the situation where we had two glass slides with like a tape put in between them. So if you did that experiment, then you know what I'm talking about, the Fizeau fringes, which are fringes of straight lines, typically that appear between the in the wedge between two glass slides or plates, etc. But so in the Michelson, we can make the fringes go from circular to straight by just slightly adjusting the angle between the mirrors. And you won't see the circular until the mirrors are perfectly parallel to each other. Okay, that's when you know that you have perfect parallelism between the two mirrors. You can also make other shapes. Okay, elliptical, hyperboloidal, all of these can be obtained, but just by adjusting some of these parameters of the mirrors. Yes.
So no matter what shape it is, so we can always like when we want to count the wavelengths like we do in our labs 2 weeks ago, and then we can always counting how much fringes passes our site.
Yeah.
No matter what shapes are.
That's true. That part will be true. Yeah. Okay, and so there are many applications. So the first one is measuring the coherence length. Remember, we have talked about coherence length before, that whenever the path length difference exceeds the coherence length, there will be no interference. And because we can adjust the distance between the mirrors very, very finely with a micrometer, we can slowly change the path length difference while observing the fringes. So we just discussed as D decreases, the fringes will move towards the center and disappear, or I increase them, fringes will move away from the center, and you'll get new fringes appearing at the central point. Okay, but the point is, once I go past a certain distance D, which exceeds the coherence length of the source, I'll no longer get a fringe. I'll no longer get fringe patterns. The fringe patterns will wash out. This allows me to measure the coherence. Is that clear? You know how we do that? Another application is I can measure refractive index of any material. Typically, for example, materials that are especially hard to measure, the refractive index is gases. Okay? Because they are almost so close to 1 that it becomes very difficult to actually accurately measure the refractive index. But with a Michelson interferometer, we can do it. And I will now work through an example, or have you also think along with me on this example, which says, how do we measure the refractive index? Here I'm taking a sheet of glass, but you could imagine doing this with a cell. Usually this is how the refractive index of like gases is measured, and this is an experiment that is one of the special projects that you can do, where we take a cell meaning like basically something that can be evacuated, and then we take out all the air in the cell, and then we introduce, say, a gas, say helium or argon or neon, etc., different gases. And remember, all of them are pretty close to 1, the refractive index for air. So how do you measure the refractive index in normal situations? You can't just take them and put like a beam through and do it like the way you did in your first lab. You don't see any change in the path of the beam at all. It's very hard to measure that. But now we can measure it using the Michelson interferometer, as shown here. I'm going to just do it with a sheet of glass, but we can do it for the cell of some gas as well. So a sheet of glass with certain thickness is inserted into one arm of a Michelson interferometer, illuminated by a yellow lamp. Okay, and the wavelength of that yellow lamp is 587.56 nanometers. Okay, how many fringes will be displaced, and in which direction? Okay, so let's work through this problem, and I'll have you also think along with me. Let's see. Okay, so let's talk about how to first think about this problem. So we draw the Michelson interferometer. Just a very crude drawing, but doesn't matter. Okay, so here's the mirrors. I just put this sort of, these to denote that these are mirrors and this is a beam. Okay, so M2, M1, or M1, M2, doesn't matter. So we have light is going through here, goes here, and they all recombine down here, and this is my detector. Okay. And let's say that initially there was some path length difference. We don't know what it is. There was some fringe pattern. Again, we don't know what it is. But now we introduce a piece of glass with some refractive index M and some thickness T. Okay. This is the piece of glass. I just put it into that part. So what is the change in the path length that occurs due to this piece of glass? You want to talk to your neighbors, come up with an idea for what it might be. How would I find the path length here that changes? I mean, nothing changes, right? Geometrically. The beams have traveled the same distance in both situations. So why do I think that there is a change in path length at all?
Because there is a reflection that change. Because there is a reflection that changes reflection of mirror. That
isn't right.
There are two.
Imagine that this is a perfect piece of glass, and I somehow eliminated all the small ghost reflections from it and all that. Ignoring that, is there a change in the path length for the beam, the geometric part, when it goes through the piece of glass? So if initially the path length difference was D or 2D, as we discussed, because the mirrors were, say, apart by D, after putting in the piece of glass, does the geometric path length change when I put the piece of glass in? What do you think? I'm going to put Anika on this one. Yes. We are among friends.
I don't really know. I was just gonna guess and say no.
Yeah, you're right.
Okay.
The geometric path length doesn't change, right? I mean, the beam went through that section already once before the glass was introduced. Now the glass is introduced, nothing has changed. The beam still goes through that same piece, same path. So what is changing? If that refractive index is no longer 1, but is some other value, what exactly is changing for the wave in that section? Now I ask you to think about, you can think about this in many different ways, but imagine there's a wave. Here's the wave, I'm drawing it, spatially, right? That's the wave. Here's another wave. Does anything change in the glass? Yes.
It's speed.
It's speed. And what does that imply for the wave in the spatial drawing? If the speed has changed? Yes?
The wavelength.
Wavelength, exactly. Very good. So the wavelength has changed, right? Which means the phase then has changed inside that piece of glass. Okay? How much has it changed? There's a name for this change, for this extra path. The geometric path length didn't change, but something else has changed. Optical. Thank you. Thank you for that one. Right? Optical path length is n times geometric. I mean, you may wonder again, why do I introduce this? Well, I mean, I can also talk about it in terms of the wave. Basically, I can say that cosine of 2 pi over lambda naught is the thickness of that piece over there, right? So the phase of this wave, ignoring the cosines and all that, the phase of the wave, if I didn't have a piece of glass, then it would be just 2 pi over lambda naught times t. But when I introduce the phase, the piece of glass, now it's 2 pi over lambda glass times t, which is now 2 pi over lambda naught times nt, where n is the refractive index of the glass. So the path length in the glass is now n times the thickness of the glass. And remember, the wave travels through that thickness twice. So it's 2nt. Okay? So the extra path length, so the optical path length due to the glass is 2 times n times t. But remember, originally, that same area where the glass has been introduced had air in it. And so that must be subtracted to find the difference between the two situations. We want the difference, which means I must subtract 2 times the thickness. Because where that glass was just air, which I'm assuming has refractive index 1. It's not strictly true, but it's fine for our purposes. Okay? So 2nt minus 2t is the path length difference, optical path length. Is everyone okay with this? Why is 2nt minus 2t? It's very critical. So, okay. So this is just 2t, which is the geometric path length of that glass, times n minus 1. Okay. So now we see how to calculate the refractive index. When we observe the number of fringes, okay, let's say that we had, say, so this I'm going to call the optical path length just to avoid having to write it every time as delta times the big lambda. Remember, big lambda represents the optical path length. So delta lambda, big lambda represents the geometric, the change in the optical path length. So if I want, say, a bright fringe to go from here to here, I need to introduce an extra wavelength into the system, right? One more wavelength of path difference. So when delta lambda, so for example, if delta lambda is equal to lambda naught, I would introduce one more fringe into the system. If delta lambda naught was 2 lambda naught, I would introduce 2 bright fringes extra into the system. So on and so forth. Does that make sense? Okay. So if I introduce, say, m lambdas into the system, m fringes will go by. New fringe will appear in the center, and then the old fringe will be pushed outward, a new fringe will appear. So if I'm looking at the center, I'll watch as more fringes travel outward, or if I look at any point not right at the center, I'll see the fringe move outward from my vision perspective, and it'll travel. Let's say I count the number of fringes and I say I get 10, then I'll put m equal to 10. Okay, the 10 bright fringes went by as I was watching this glass getting inserted into the system. Okay, is this all clear to everyone? Yes? Okay, so then to conclude, we want the number of the fringes to be just delta lambda divided by lambda naught. And that is just 2t n minus 1 divided by lambda. And so since we have all these numbers, the thickness, the refractive index, and the wavelength, we can then calculate how many fringes will go by. And also, as I already talked to you about, it will be outward from the center because we're introducing new fringes. We're increasing the path length that adds in new fringes from the center. Okay, so I'm out of time. So what I'll do is in the last few minutes, let's do one question from the pop quiz so that you folks have that extra benefit of coming into class. Maybe that'll encourage some of the other people to come.
It's pop quiz